So today we'll continue our discussion on um, sort of the general properties of mode that we started last time. Right. So, for example, we were discussing that there is this orthonormality condition, right? Uh, so in general, like as we said, like for a mode propagating, so it could have some profile psi of x comma y and propagating in the z direction, right? So if you take this integral over the cross section xy, then this is 0 if you take two different modes, right? And if it's normalized, then it's 1 when you consider the same mode. Right? So let's look at so this basically comes directly from the wave equation that we solved to get the modes, right? So as we know, for like planar slabs, there is no y dependence, right? So for that, like we just have the integral in one dimension, right? In that. So right. So let's see explicitly where this comes from. So again, going back to the equation that we solved, right? So we solved this homogeneous wave equation, right? Right. So this n square of x, for example, for a step index was n1 in the core region and n2 in the cladding region, right? In general, it could be we'll see the next topic where we consider gradient index waveguide. So this would be like a function of x, could be in general any function of x. Okay, so yeah, that's the equation we started with, right? And basically the solution beta I for the ith mode gave us basically the properties of the ith mode, right? So basically this is an eigenvalue equation, right? So if you write it like this, okay, so this you can see basically looks like the Schrodinger equation for quantum mechanics, right? So you have a double derivative with respect to position, right? So that represented the kinetic energy in quantum mechanics, and then you have something times the mode function. So there you have like the potential function. So this refractive index profile is basically like a potential, right? And then the solution. So in the quantum mechanics case, you have energy here, right? So here beta I, the solutions for the propagation constant correspond to sort of the eigenvalue. So we can write this for another mode, like the jth mode also, right? So just replace I by j, and then we take the conjugate, right? So remember, basically we want to show something like this, right? So take the product of one mode conjugated with another mode. So let's write the equation for the other mode. So here everything is real, so only the mode function gets conjugated. Right? So now basically we have these two equations, right? So since we have something like a product, right? So what we do is multiply this first equation by psi j conjugate, multiply the second equation by psi I. Okay, and then subtract. So subtract this equation from this equation after this multiplication. So we get on the left hand side okay, and of course on the right hand side it's just the difference in the propagation constants times that. Right, so now if we recognize this thing on the left hand side, right, that's nothing but that, right? So you can see, just check, this is basically just equal to that, right? So the double derivatives survive and then the cross terms with single derivatives cancel out. Okay. And then yeah, right hand side we have the same thing. Right, so again, we want to evaluate this integral of this psi I conjugate psi j, right? So we have something like that here. So let's just integrate then both sides. So basically integrate both sides over x. So multiply by dx, right? Here also times dx. Right, so now this integral you can see, so we have a d by dx already, so that cancels with the dx, right? And we just get these functions evaluated at plus minus infinity. Right, and on the right hand side we have this integral, the orthonormality integral that we want to evaluate. Right? So this thing, right? So this is basically the mode function evaluated infinity multiplied by the derivative of the mode function for another mode at infinity. But when we solve for the modes, for physically relevant modes, as you know, basically for any mode m, basically as x tends to plus minus infinity, this has to go to 0, right? And not only that, the derivative also has to go to 0, right? Because remember, so for example, if we solve for TE modes, then we solve for the electric field. So these would be the solutions for the electric field, and then the magnetic fields will be given by the derivative. Right? So all fields have to decay to 0, right, at infinity. So the derivative also has to go to 0, right? Which means both these are 0. Right? So this is 0. This is 0. So that means the right hand side is 0, right? So right hand side 0 means either beta I is equal to beta j, in which case I is equal to j, right? Or this integral is 0, if I is not equal to j, right? So basically, which is this orthonormality, right? So you can see that anytime you have an equation like this, right? Some double derivative times some function of x, right? We didn't really use any properties of this n of x. It could be anything, right? So it just comes from the general form of this equation, right? That's why also in quantum mechanics you see the same condition, right? Whenever you have a differential equation like this, with these conditions that the field should decay to 0, then you will always get this orthonormality condition. Okay, so these are for guided modes, where basically I and j are like integer values, right? Discrete modes. For the radiation modes, right, which correspond to beta, which are not solutions of this equation, basically you can define a similar kind of condition, but now it's beta can take continuous values, right? So now this is the delta function, not the Kronecker delta, but the actual delta. Because beta can now take any continuous range of values. So this would be for radiation modes. Okay, this orthonormality condition is actually very nice because, as we will see, basically what it ensures is that the power in each mode. So at the input we launch some particular field profile, right, which basically launches some particular modes. But this orthonormality condition ensures that there is no sort of mutual coupling between the modes. So the power in each mode remains the same as the mode is propagated. Okay, so there is no mixing. So for example, then if you want to encode information in the different modes, they'll all travel parallelly without any sort of crosstalk. Okay. I mean, that's theoretically true for a ideal waveguide, right? But in practice, as you know, for example, if you make very long fibers, there are very tiny variations, for example, in the core along the length, right? And so basically what that means is that this cross section is not exactly the same along the length, right, which we assumed in solving this. So when the cross section is varying slightly, then you get sort of some coupling between the modes, and then you can actually transfer power between modes. We'll study that probably in more detail towards maybe the latter half or the end of the course. Okay? But if you have an ideal waveguide where the cross section is not changing, then we have these orthogonal modes and there is no coupling. Okay, and then so in this case, for example, we saw that each mode corresponds to a different beta, right? As if you change the mode index, you get a different beta. In some cases, depending on the symmetry of the waveguide, right, some modes could be degenerate, right? Which means for two different modes, you could have the same beta, right? So that depends on the symmetry of the structure. So for example, so when we study optical fibers next, right? So you have circular symmetry, right? So any rotation, so if Z is coming out of the board, which is the propagation direction, any rotation in the XY plane leaves the structure invariant. Right? So then you can imagine that there is no difference between, let's say, a mode which is X polarized. Right, so let's say this is X and Y. So you could have a mode, let's say, which is the electric field is polarized in the X direction. You could have an equivalent mode which is polarized in the Y direction, right? And there is no difference because it's just a rotation. Right? So they should have the same propagation cost. Okay. So these would be two different degenerate modes, right? And you can ask the question, why not in some other direction, right? Any other direction can be written as a superposition of these two modes, right? So that's not like an independent mode. So you have two independent modes which are degenerate, right? So depending on the symmetry of the structure, like for example, if you had a square cross section, that again the same argument will hold, right? This and this would be degenerate. So depending on the symmetry of the structure. In the slab case, remember they were not degenerate, right? Because there was structuring in the x direction, but no structuring in the y direction, right? So a y polarized electric field mode is different from, so the TE mode is different from TM mode, right? They are different betas. But again, when we saw that if we go to the weakly guiding approximation, so when this index contrast tends to 0, then the TE and TM modes become degenerate, because then now the two directions start to look similar. Okay, so that's one thing that you should keep in mind. Depending on the symmetry of the waveguide structure, you could have degenerate modes. Okay, and then finally, basically this set of functions, right? So you have some mode functions here. So a discrete set corresponding to the guided modes, and then a continuous set corresponding to the radiation modes. So if you take all these functions, basically they form a complete set, which means that you take any arbitrary function, you can write them as a superposition of these set of guided modes and radiation modes. Okay. Again, recall maybe if you've done a basic course in quantum mechanics, it's the same thing there. Okay. So any general function can be written as a superposition of these modes. So basically, how does that condition help us here is that we can calculate what is the, so for some particular field profile that we launch at the input, we can calculate how much power is present in each mode. Right, and then we saw because of this orthonormality condition, basically the power in each mode will remain constant, right, as along propagation. So basically, so that is known as the completeness condition. And basically the finite set of guided modes right, so let's say we have some n number of modes depending on the parameters of the waveguide, right? Then you have those n modes and corresponding mode profiles psi I of x or x comma y, and then the infinite set of radiation modes, right? So all those betas which are not solutions. Basically, these two together form a complete set. Right, which means that I take any arbitrary function, right, in space. I can write it as a superposition of the guided modes, so sum over the guided modes with some coefficient ai. And a superposition over the radiation modes. So this is now a continuous set, so we perform an integral. Okay, so if I take any arbitrary function, anything at all, I can write it as a superposition of these guided modes and radiation modes. And for each different function, these coefficients ai and a of beta will be discussed. Okay, so again, like we are coupling from some free space into a waveguide, right? So let's say I launch some arbitrary input field profile here, right? So at z equal to 0, my input profile is some e input x comma y comma 0, right? Depending on what focusing optics I use to focus light at the input of the waveguide, right? So that profile I can write as again a superposition of. So remember, these things are just so for the guided modes, you can write them as some e of x comma y e to the I minus e to the I, right? Hello, sorry, there was some Wi-Fi disruption at my end. Can you all hear and see the board also? Hello, is the video and audio back?
Yes, sir.
Okay.
Yes, sir.
Okay. Um, right, and then what is the strength of each mode uh, that is launched? So these coefficients, right? So that we can find out from this orthonormality condition, right? So if we multiply by EI conjugate and integrate, then we'll see that all the other modes will become, like the integral will be 0, right, from the orthonormality condition, and only the, so basically if you multiply by, so the jth coefficient aj is just right, you multiply with the mode profile of the jth mode with my input field profile and integrate, and you get the coefficient, right? Because that's the only thing that will remain. Everything else will integrate to 0. Similarly, for these coefficients of the radiation modes, you multiply by right, and remember these are just solutions to my wave equation, so I know for a given waveguide structure what these functions are, these profiles are, right? And also I can write the radiation modes like that. So for any input field profile, I can calculate what are the coefficients here, which means like what are the powers in each particular mode, right? So right, so I basically get the fraction of power that is excited in each mode. And then on propagation, basically all that happens is you just acquire this phase, right? So Like after propagation distance z, so my output field profile I can write just by multiplying the phase factors here. Right? So basically, it looks something like this. Right, and so recall the power in a field is proportional to mod E square, right? So the powers that you are launching at the I square for the ith mode, right? And on propagation, basically just a phase is acquired. So even for after a distance z, right, the power in the ith mode is basically just the mod of the coefficient here, right, which is basically just mod ai square, which is the fraction launched at the input. Okay? So right, so basically the powers in the different modes remain constant. Okay, so we can completely calculate how the mode behaves, right? So given some input field profile, we can first calculate these coefficients by these integrals, right? So which will tell us what modes are excited and in what fractions. And then we can just propagate them by adding the phase factor. So we can find the field profile at any distance z, right? Right? And because of the consequence of this orthonormality condition, we see that the power in each mode remains same. There's no mixing. Right? Just each mode acquires a phase at a different rate, but the powers remain the same. Okay, so this is a very powerful result, basically, that, for example, allows you to encode information in different modes. Okay? And then you can also choose your input field profile optimally such that you excite, for example, the mode that you want with maximum power. Okay? So, for example, if you want to excite guided mode with maximum power, you want to make sure these integrals are 0, right? And this integral for particular j that you want to excite is maximum, right? So you can choose your input field profile accordingly. Okay, so yeah, that we finish discussion on sort of the general properties of mode, which are true for any waveguide, not just planar waveguides, optical fibers, or any waveguide at all. And as you see, also true in some other systems which basically have the same equation. Right? Any questions? Okay, so last couple of classes, basically we solved the modes in a step index planar waveguide, right? But we could also have graded index planar waveguide, right? Where this n of x is not constant in the core and cladding, but it could be some function, continuous function of x. For example, ray paths in such graded index structures. So let's just briefly see how we can actually solve for modes in such structures. So yeah, this topic is a gradient index planar waveguide. Right, so imagine again now you have some slab of thickness d, right? But now the refractive index is some continuous function, right? So this is n of x. So for step index is a constant, right? And then in the cladding it is some lower value. But for gradient index it's some continuous function, right? So this refractive index is recall just the square root of the dielectric constant. So this is some inhomogeneous medium now, okay, where the dielectric constant is a function of position. So recall that when we were deriving the wave equation, so the coordinate system, write that again. So z, this is the propagation direction, x is the transverse direction, y is converted to volt. So the wave
the refractive index of say flint glass, and where I had
is it back now? Yeah, sorry, I don't know. There seems to be some problems here in the IIT Wi-Fi. Okay, so yeah, so recall that when we were deriving the wave equation, right? So we had a term which we neglected for the homogeneous media, right? We had this term which depended on the gradient of the dielectric constant. Right, so this we basically said, okay, if we have a homogeneous medium where the refractive index of the dielectric constant is independent of position, then this term is 0. Right? But in a general inhomogeneous medium, of course, now because epsilon is a function of x, so gradient of E epsilon is non-zero, right? Which means this term in general could be non-zero. But actually, if you look at this special case here, right? So in this case, epsilon is only a function of x, right? Which means, so when we take the gradient of epsilon, that will be in the x direction, right? Because the gradient is basically takes the derivative with respect to the position coordinate in that position direction, right? So since it's a function of x only, gradient of E, so this is basically just del E by del x, x cap, right? epsilon. Right, so this term is something parallel to the x direction. So now if we consider, for example, a TE mode, right? So there we consider E which is in the y direction, right? So in that case also you can see this dot product will actually be 0. Okay, so this term goes away and we end up with the homogeneous, sort of the homogeneous wave equation, except now this will be a function of x. Right? So for this particular profile, right, where the refractive index is only changing in the transverse direction and I consider a mode where the electric field is polarized perpendicular to that, then this inhomogeneous term still is 0. So for the TE mode, I can still write the same equations, right, that we had. Okay, so for the TE mode, even for an inhomogeneous medium, I end up with the same equation. It looks like the homogeneous wave equation, but now this is a function of x. And same argument you can make for the TM mode. So there you write the wave equation in terms of h. Okay. And again, if you do that curl and try to derive the wave equation in terms of h, you'll get a similar term. And again, if you consider TM mode, where h is in y direction, then for the TM mode, I can also write this kind of equation, but for h. Hello, yeah, the connection got disrupted again. I hope it's back now.
Yes, sir.
Yeah, I don't know what's happening actually. It keeps the on-campus Wi-Fi is behaving strangely. But anyway, So, right, so we can use the same wave equation, right, to solve for the TE and TM modes, right? So again, for example, for TE mode, we take E like this, right? Right, some so polarized in the y direction, some field profile which depends on the x direction, and then this phase omega t minus theta z. Right, so basically we can plug in this kind of solution into the wave equation here. Right? Same thing that we did for step index. So we get the same equation here, the second order differential equation for Ey. Right, same equation here. Only difference is now this here n square of x is some continuous function instead of being like n1 square in the core region and n2 square in the cavity. But this equation has the same form. So basically you can try to solve this differential equation for any arbitrary n of x, right? And the solutions will give you the modes for those, right? So in general, of course, for any general n of x, it may not be possible to solve it analytically. So in general, you require like numerical techniques to solve it. But in certain special cases, you can solve it exactly. Okay. So, for example, if we take the square law medium that we had discussed previously for the ray paths, right? So n square of x is a parabolic function, right? Like that. Okay, so if I am writing like that, then this is like 2a, right? So I think this is 2a. This is a and minus a. Okay, so this function is like a parabola, you can see, right? So at x equal to 0, it is n1 square. So n of x, so here it's n1 at x equal to 0. And then it reduces by, so this factor 1 minus 2 delta at x equal to plus minus a, right? So an actual structure, of course, so it will terminate at a and then like have a constant refractive index, let's say in the cladding. Okay. So in general, if you want to solve for something like this, again you have to solve two different equations, right? One like this in the core, and then the other one, remember, in the cladding, and then use boundary conditions, right? But for this inhomogeneous thing, that gets too complicated. But we can get very good approximate solutions by assuming that this profile actually just extends forever. Okay, so this is for all x, not just between x plus minus a. So of course this is an approximation to this profile, right? But this works very well when the modes are well confined into the core, right? So if the modes are not seeing much of the cladding, right? So the power here in the cladding is very small, then this approximation works very well. Okay. So for example, let's say you had a waveguide which supports some n number of modes. For the first 2-3 modes, right, they will be most well confined here, and for those, this approximation will be work well, right? So as long as you're considering modes which are tightly confined into the core, you can just assume this profile to extend to the front. Okay. But once you start, if you want to consider modes which have significant fraction into the cladding, so higher order modes, then you have to solve like separately and do boundary conditions. Okay, but let's just look at the solution for an infinitely extended parabolic medium like this. which is sort of easier to solve. Okay, so we can just plug in this profile into here. Right, so when we were discussing ray paths, we discussed sort of like why the parabolic profile is important, right? So we'll see, so in optical fibers also, this parabolic profile is sort of a popular gradient index optical fiber. So if you plug this into here, right, you get that. So this factor here, we sort of rewrite it like this. Okay. So we sort of first combine the constant terms here and write the x dependent term separately. And then we define this thing constant here as alpha. So this alpha is k0 n1 square root 2 delta divided by x. So it just depends on the waveguide parameters, right? Thickness, index difference, maximum index in the core. Right? So if you take alpha out common here, so divide everywhere by alpha or alpha square here and alpha square here, right? So we can define a change of variables. So this is xi equal to alpha of x, and you can rewrite this differential equation in terms of this new variable. Okay, like just that. Okay, and this capital lambda here, this is k0 square minus beta square divided by this alpha square. Okay, so we end up with this simple looking differential equation here that we need to solve. Right, so again, beta would be the solutions. Right, so again, you can think of this like an eigenvalue equation. So if you take this capital lambda to the other side, then I have some differential equation in Ey on the left hand side, and then some constant times Ey on the right hand side. Right, which that constant depends on beta. So that's the eigenvalue. Right, so in order to solve that differential equation, so that's like a standard differential equation that one encounters in many areas of science and mathematics. So basically, to solve that, what you do is you first do a substitution like this. Okay, so we write the solution EY as product of this Gaussian function e to the minus phi square by 2 times some other function. Okay, and we substitute this into this differential equation. And so first you have to evaluate, so do the substitution and then find out, so first find out what dy by d psi is, and then second derivative d square by d psi square. Right, so we get multiple terms because both these are functions of psi. So basically, yeah, so you evaluate this in terms of u, and then here also you just plug in ui in terms of u. So after you do that and simplifying the terms, basically you get a differential equation u. Okay, so do this at home, right? So do the substitution and plug this in here and confirm that you get this equation. A polynomial function like this. Right, so for example, this, in some cases, this could be the Taylor series expansion for some particular function. Right? So, yeah, we just plug this in here. So first term you have a double derivative, so that will reduce this power by 2. Right? So the first term you'll have terms from 2 to infinity because the 1 and 0 and 1 terms will just go away because of the double differential. So you get r times r minus 1 for the double differential. Right? Power reduces by 2. Second term, power reduces by 1. You get r times psi r minus 1. Right? And then, of course, constant term here. Okay, so basically you can write this thing, right, as right here. So a sum going from 0, instead of 2 to infinity, going from 0 to infinity, and just rewrite it like this. So r plus 2 times r plus 1, ar plus 2, psi to the r. Right? So it's the same thing here. I just shifted by 2, so that the sum starts from 0. Right, so if this whole thing on the left hand side is equal to 0, that means the power of each term, right? So on the left hand side are different powers of psi, on the right hand side are just 0. So all the coefficients of all the psi to the r should be 0, right? For this identity to hold. So we can just write that condition for each r, right? Right, basically, so our task is to find what these coefficients a of r, right? If we know that, then we can write down this polynomial and we know the function, right? So if you do, so first term will be psi to the 0, which is the constant term, right? So the constant term on the left hand side you can see is 2 times A2, that comes from here. So R equal to 0 term here will give me 2 times A2 plus lambda minus 1 A0, right? That comes from the constant terms here. This is not giving me any psi to the 0 term. Because this psi I can take it inside, right? And then this power goes up by 1. This I can write like that. Right, so here the terms start from psi to the 1 only. So there's no psi to the 0 term here. So that we get from the constant term. And if you now look at any term greater than or equal to 1, so right, so now, so this is for any other r. Right, so we just look at the coefficient of psi to the r, right? So the coefficient of psi to the r here is r plus 2, r plus 1, ar plus 2. Second term here is 2r times ar, and here it's lambda minus 1 times ar. Okay. Plus. So here you can see we can get a relation between ar plus 2 and ar. Right, so ar plus 2 so we get like a recursion relation between successive powers, right? So for example, I can start with A0 and then find out A2, and then from A2 I can find out A4, A6, so on, right? Or if you start from A1, you can find out A3, and then A5, A7, right? So yeah, so basically we can find out all the coefficients from this recursion relation. Yeah, so looks like we are out of time. So next time we'll continue. And so from this recursion relation, we'll see what the coefficients look like and what this function is, and then look at the solutions. Yeah. Any questions?
To infinity or r equals to 0 to infinity?
Sorry, I'm not. Your voice is. Can you increase the volume a little bit, or speak louder?
Hello?
Yeah, go ahead.
Yes. So, sir, the second term, you wrote the summation runs from 1 to infinity, or is it will it be 0 to infinity? Because we are taking the coefficient zeta.
This term?
Yes, sir.
Yeah, so this comes from here, right?
No, the summation. So
Yeah, no. So you plug this into this equation,
yes,
right? So, I mean, since you have an r here, you can see that r equal to 0 is anyway 0, right?
yes.
I mean, you can write it as from 0, doesn't matter because you have an r here, so anyway that term is 0.
Okay.
I don't know if that's your question.
Yes. Okay. Got it.
But this is sort of general technique to solve. This comes up in many places in different fields of science, right? This kind of equation. So these coefficients here with the differential operators could be slightly different, right? But you end up with these kinds of equations quite a lot, and a general way to solve them is assume a polynomial solution. And for different equations, you get like different kinds of recursion relations, which means the function that you finally get will be different. So in this case, for example, we'll see that what we get are Hermite functions. Okay, so U will be Hermite functions, which means this solution for the field profile here will be Hermite Gaussian functions. Right, so in the step index guide, we got like sinusoidal solutions in the core and then exponential decay in the cladding. In this case, we get Hermite Gaussian solution. So these Hermite Gaussian functions are very common, right? I mean, for example, you might have seen them in already in again your basic quantum mechanics course. If you have a simple harmonic oscillator with a parabolic potential, then the wave function solutions are Hermite Gaussian, right? So it's the same thing. Basically, we end up with the same equation.
Yes, sir.
Here also we are taking the refractive index profile to be parabolic, which is equivalent to taking a potential which is parabolic in the Schrodinger equation case. Right, so if you change the potential, then this equation that you'll end up will be different, and then your solution. But it's sort of like a general way to. Not in every case will you be able to find such relations, right? Only in some particular refractive index profiles will you be able to get nice relations like this to finally get an analytical solution.